In last class, basically we go through the finite element method for the nanowire and through the create the geometry for the nanowire through the GMIS and visualize the conduction band edge and quantum dot region also. In today class, basically we go through the atomistic package, like finding the band diagram for the silicon, germanium, and finding the eigenstate, eigenenergy, and value splitting through the atomistic package. And apart from that, we also go through the fully depleted silicon-on-insulator for single quantum dot array and create a geometry file through the QTCAD builder option, like through the Python code. We create the geometry file. After that, we use the Poisson and Schrodinger simulation for finding their property related to that, their conduction band edge and band diagram and quantum confinement region, their quantum dot region, and other properties also. As we know, Impulse technology provides the simulation software for the material simulation, like TFT based, NEGF based, like analytical and rescue software. And apart from that, we also offer simulation software for the quantum computing, solar cell, and hardware equipment for the solar cell also. And we offer simulation software for the quantum material and simulation tools. We offer on the cloud also and on the HPC also. And you can see our partner are Fluxim, Nano Academic, and HZW. Fluxim offers simulation software for the solar cell, like you can use for the perovskite, tandem solar cell, OLED, QLED, and you can do for the solar cell large PV modules. And it included two software. Here you can see SetFOS and Laos software. SetFOS used for the perovskite solar cell, photodetector, and LED. Laos is used for the large area solar cell, like advanced optical solution software. Nanodical is used for the material plus device. It means you can simulate the nanomaterial and nano device structure. It is based on density functional theory and non-equilibrium King function. Here you can see the rescue software, which is based on density functional theory and density functional perturbation theory. In rescue software, you can simulate large number of atom of material you can simulate, like up to 20K atoms you can simulate in the rescue software. It supported CPU plus GPU acceleration both, and you can use the plane wave basis set also here in the rescue software, and numerical atomic orbital you can use. And QTCAD, you can do for the spin qubit devices, superconducting circuit properties also through the QTCAD software. It is basically for the quantum device design structure. And nanoscale is used for the tight binding method for the device structure. FD-SOI is also used for the material simulation. It is based on plane wave, and you can find the property like AIMD, NAB method, molecular dynamics, and multiple properties, electronic properties you can find through the FD-SOI software. And if someone working on the quantum chemistry, they can use the BDF software, where can they use the time-dependent DFT and other properties also through the BDF software. And you can see our customer list here, like top institute of India, you can see here, like Nice Gurgaon use the solar cell software like SetFOS and Laos. BIT also use the material-based simulation software like NanoDecay Rest, and some of them using QTCAD as a trial version now for research papers. Now let's talk about the QTCAD software. In the last class, we discussed about the QTCAD supports multi-scale simulation. It means you can simulate any device structure at atomistic level also and finite element method also. Like you can do for the atomistic and quantum modeling both. It supports Schrodinger and Poisson solver. In Poisson solver, you can do the nonlinear Poisson equation also, and it supports finite element method. You can do for the spin qubit and quantum dot simulation. You can find property for the superconducting circuits like capacitance matrix, Maxwell eigenmodes, and resonator capacitors. Different type of property you can find through the QTCAD software, and it also supports high performance scalable also. Now, in the last class, we discussed about their API structure, like it support device builder, transport simulator package, and qubit simulator package. Like in device package, it included different module like mesh module, device module, solver module, auxiliary module, and post-processing module. In the mesh module, we can import 1D mesh structure, 2D mesh structure, and 3D mesh structure. In the device module, you can define the material, potential, density, and the wave function. In the same way, you can see some of the solver here, like Poisson linear solver, non-linear Poisson equation solver, Schrodinger solver, strain solver, multi-value effective mass theory solver, and quantum well, lever arm matrix, many body solver also included. That means to import these all modules, you can find the quantum mechanical properties also for any quantum device structure. And apart from that, you can see some other modules also, like constant to define the elementary charge constant, Planck constant, Boltzmann constant. It already defined in the constant module. In the same way for the material also, there are some predefined material are present in the QTCAD software. You can use directly like silicon, germanium, and different type of material you can use from the material module. Apart from that, you can define your own material file by defining their property like dielectric constant, electron affinity. There are different type of property you can define through the predefined user defined material. In the same way for the quantum also and some operators also. And if you come in the transport simulator, you can find the transport properties like IV curve, charge stability diagram, master equation solver, and you can do for the NEGF Poisson equation also. Like it support NEGF also. And you can do for the WKB lead classes also. And in the same way, qubit simulator also supported, where you can find qubit dynamics, gate fidelity. You can do for the noise properties also, and EDSR also. Like you can find Rabi oscillation and electric dipole spin resonance. You can do in the qubit simulator package, and you can see your result in the different format. Like it support HDF5 format, VTO format, and text format also. Like you can save your like line cut along z-axis energy in the text format, in the VTO format also, and in HDF5 format also. And apart from that, there are other two packages like builder package to create your geometry file. To the QTCAD builder, you can create your own geometry to the different text file, OS file, and you can draw a 2D layout design in the K layout. And after that, you can directly import into a QTCAD builder option, and you can create a head to structure. Like first, you have to create a 2D layout in the K layout. Once you import the OS file, you can directly import in the QTCAD builder option, and you can create directly head to structure. Like for the fully depleted silicon-on-insulator, you can create a 2D layout in the K layout, and after that, you can through the QTCAD builder option, you can create a proper head to structure for the fully depleted silicon-on-insulator. And after that, you can create a mesh file and perform a QTCAD operation, like there are some quantum mechanical operation like Poisson solver, Schrodinger solver, Coulomb blockade, lever arm matrix solver. In the same way, it also included atomistic package, like where you can do the atomic structure building, you can do for the tight binding method, and you can find like density of state, projected density of state. Now let's talk about like the atomistic package. In the atomistic package, you can build your structure also through the disorder, roughness, and alloying also. You can relax through the Keating-Wallace force field theory. Here you can see resolve strain using Keating-Wallace force field theory. You can do the tight binding Hamiltonian, and you can analyze like wave function operators, G tensor also, and other property you can find. And it supported both FEM also and tight binding. It means you can find G tensor, value splitting through the finite element method also, and through the tight binding method also. For a time being, it supported 3 basic set you can see at the bottom, and you can do the support material file you can see here, silicon, germanium, and silicon germanium. Like if you use the atomistic package, first we have to create a unit set, like through the zinc blend lattice structure, like for the silicon and for the germanium also. After that, you can introduce the rough surface, and it will create an atomic structure where you can do the relaxation through the Keating-Wallace force field theory, and you can find properties also. And you can see the supported material here. And you can do the tight binding method, like to find the spin orbit coupling, surface state treatment, magnetic field, and multi-scale coupling you can do. And you can find like G tensor solver also, operator and matrix element, wave function, and dot analysis you can do in the QTCAD atomistic package, and you can visualize in the BTU format also. There are some tutorial given in the documentation also and in the software folder also. Here you can see some key capabilities of the software, atomistic packages, like you can do the strain and relaxation also. You can do the multi-scale coupling. It means you can simulate at finite element method and atomistic package also. you can find spin orbit coupling, and you can introduce the tight binding method to the basic set also. And you can see first we have to build a structure, and after that we have to relax and applying the tight binding Hamiltonian to find the electronic states. Now let's move to the QTCAD software and find the properties also for the silicon and germanium. Let's open the VS Code directly. And everyone, please open their QTCAD folder. And in hands-on training, create a Python file, Jupyter notebook basically. I hope everyone create their Jupyter notebook with the name atom.ipynb extension. Once we create, you have to click on this code section and you have to choose the kernel here, select kernel, and you have to choose the QTCAD here. I hope everyone had completed up to here. Please confirm. Okay. Now let's move further and import some library. Import NumPy, and we have to import the matplot library also, like for plotting the crystal structure. From the QTCAD Atom Package, we have to import unit cell, and we have to import here unit cell. Now we have to import wait, from QTCAD atoms. We have to import atoms. And now we have to import the gating solver for the relaxation. Again from the QTCAD Atom Package. We have to import solver as a gating solver. Now we have to import a Schrodinger solver to find the eigenenergy. From the QTCAD Schrodinger solver, we have to import solver as a Schrodinger solver. Now again we have to import a solver parameters for the Schrodinger. Again from QTCAD Atom. we have to import solver parameters. As a Schrodinger solver parameters. And at last, we have to import a constant module from the device package. First, we have to import some important libraries like NumPy, and after that, we have to matplot to plot a crystal structure. And after that, from the atom package, we import a unit cell like unit cell zinc blend. You can see the property also like unit cell of a diamond or zinc blend crystal structure expressed in the term of finger seed cell and conventional unit cell. And after that, from the QTCAD atom package, we have to import the atom modules to define the atomistic, like for the silicon and germanium. In the same way, you use a Keating solver module for the relaxation, structure relaxation, you can see here within the Keating valence field, force field model. And after that, we import Schrodinger solver to find the Hamiltonian calculation operator and the eigen solver also, you can see here. Same way for the parameters also. And at the last, you can see we import the constant module to define the elementary charge. You can see here, like mass of electron, elementary charge, Planck constant, Boltzmann constant, vacuum permittivity. You can see multiple constants have been defined in this module function. Once it complete, we have to run this. Let me save first. Now you can see it completed successfully. You can see that the bottom section also, like the QTCAD version and some other properties here. Now click on this plus code section. I hope everyone had completed up to here at the top section to import the library. Please confirm. Okay. Now let's move to the bottom section and create a unit cell for the silicon and germanium. For that, we have to create unit cell. We have to create unit cell zinc blend, and we have to define here lattice constant. And we have to define the atomic species here. And we have to define here silicon. Now do the same for the germanium also. And we have to change here germanium. And we have to assign the change the for germanium, and for the above one, silicon. And we have to change the lattice constant also. Once we define the unit cell, we have to plot the band structure also. For that, we have to use the unit cell again. Plot band structure function. And after that, we have to assign the title here. And we have to assign the show figure. Do for the same for the germanium also. And save and run again this one. Now you can see the silicon band structure and the germanium band structure also. You can see first we create the unit cell for the silicon and germanium, where we define the lattice constant also, and with the unit cell zinc blend. And after that, we plot the band structure for the silicon and for the germanium also. I hope everyone had completed up to here. Please confirm. And also get the result also. Now let's move to the next code and relax the atomic structure. First, we have to create a silicon atomic structure with the 3 nanometer cube. For that, we have to assign the array here. Into nanometer, and we have to do for the same for the y also and z also. After that, we have to introduce the atoms. And we have to assign the roughness parameter here. If we in the next section, if we introduce the other materials also, we have to introduce the roughness parameters. And again, now save and run this code. Now you can see the command window also in terminal output. Atomic structure built. Total number of atom you can see here 1465. Now again we have to create next code. Again add the code cell and Now we have to introduce the kitting solver module to relax the structure. For that, we have to introduce the kitting solver here. And we have to introduce the solver module here. And we have to save the relaxed structure. For that, we have to create a path here. Silicon structure, and we have to print it relax or not. Now we have to run this code. Here you can see relaxing atomic structure. And it will save our silicon structure with the name silicon structure.xyz. For up to now, if anyone have doubt, please ask. Like if someone facing any issue, please let me know. And you can see it completed also. Save data in silicon structure.xyz, atomic structure relax, and the relax structure saved to the silicon structure.xyz. You can see here also silicon structure.xyz. And now if you want to import, let me open the our material software. And let's import the material directly here to see the structure from the QTCAD and hands-on training. You can see the silicon structure.xyz. Now you can see the silicon structure, relaxed structure. And you can see the properties also, like the total number of atoms and their chemical formula also. I hope everyone had completed up to here. Please confirm and get their silicon structure also, relaxed structure with the kitting solver module. Please confirm. Let me repeat the process again. First, we import some important library. You can see from the atomistic package, we import the unit cell module and import the unit cell zinc blend. Again, from the QTCAD Atom Package, we import the atom module. In the same way, from the Schrodinger solver, QTCAD Schrodinger solver, we import Schrodinger solver parameters. And same way for the device module. And after that, once we import the important module, we create a unit cell for the silicon and germanium. And after that, we plot the band structure for the silicon, you can see here, and germanium also. Once you compute all these things, we introduce the unit cell to create a proper cube structure. Here you can see tiling crystallographic unit cell volume for the atomic structure. Once we created, we introduce the heating solver module and relaxed structure. And once we relax the structure, we can also visualize in the any material-based software like ASE, Ovito, and other software also. You can visualize your relaxed structure. Now let's move to the next code. Again, add the code cell. And now read the atom count number. You can also use the with open function. We have to count the atoms. We have to use the F read line. And now we have to count the rows. And we have to assign the position here. And we have to print a number of atom also here, like how many number of atom present in the relaxed structure. And let's run this code. You can see the number of atom directly here, 1465. Now again, add code cell and visualize the structure also. For that, we have to assign the module here, like for matplot library. And we have to assign the colors also. After that, we have to introduce here to convert into nanometer. Same way we have to do for the Mark II also. And run this. Now we have to assign the label also. And you can see the structure also. If you have don't have any material software, you can directly plot to the matplot also. And you can visualize the silicon structure in this way. Let me give this code in the chat box. Like to see the structure for the relaxed structure. Again, we have to add the next code section here. And now we have to add the confinement potential here. And we have to add the potential here. Add. In that direction. And after that, we have to introduce the tight binding Schrodinger equation. Once we introduce the confinement potential, after that, we have to introduce the tight binding Schrodinger solver parameters. For that, again, we have to introduce a solver parameter. And we have to assign the number of state here. Here assign the number of state here 2. And after that, we have to introduce the Schrodinger solver. And we have to introduce a self-consistent Schrodinger solver. And we have to energy target to print the eigen energy also. We have to give the energy target. Now we have to print the energy also. And run this code again. You can see the atomistic tight binding eigen energy. You can see the 2 eigen energy here. In this way, you can do the finding the band gap, value splitting you can do, and G tensor calculation you can do, and you can visualize also, and you can relax the structure also through the QTCAD atomistic package. Again, I repeat, first we import some important library from the atomistic package and some device packages also. Once we import the module, we create the unit cell structure for the silicon and germanium, and we plot the band structure. You can see silicon band structure and germanium band structure. After that, we create a unit cell by defining here. And after that, we introduce a solver, fitting solver to relax your structure module. And you can see we relax structure and save in the format of silicon structure.xyz. You can visualize in any other format also, like in other software also, like Obito and ASC, you can visualize. If you don't have, you directly can write this code and count the total number of atoms also. And you can plot using the matplot library. After that, we introduce the confinement potential and we introduce the Schrodinger solver to find the eigen energy also. And you can see atomistic tight binding method here. I hope everyone had completed up to here. Please confirm. And apart from that, like if you want to see the API reference, like the every function, you have to go to the nanoacademy.com. And at the bottom section, you can see the documentation, QTCAD. And here you can see the API reference at the bottom section. And you can see the first package here, Atom Package, QTCAD Atom Package. And you can see the module here, like QTCAD Atom Analysis module. You can analyze the dot function and you can analyze the operator element. If you click on this, you can see the parameter, their return value, and the default parameters from this function. You can easily understand by looking into the module function and their parameters. Like in the same way, you can see the analysis module and you can see QTCAD atoms module. You can see the multiple function given here. Same way for the G tensor, tied binding, and kitting module, material module you can see here. And you can see the tied binding model parameters. You can see the 1 atom, 3 atom, 2 atom option, and roughness surface module also. Through this, you can easily understand the atomistic package easily, and you can find like the different type of properties also through the atomistic package. And if you want to see the theory section, click on this theory atomistic package. you can see unit cell, random roughness surface, atomic structure, valence force field model solver, and tight binding Schrodinger solver, and the G tensor solver also. Like you can see the theory part. And if you want to see the tutorials, click on tutorial. You can see the device package also, transport package, qubit package examples, and you can see the atom package also. Like the first one is doing through the finite element method, and second one is through the tight binding method. It means it supports multi-scale, and first through the finite element method, second through the tight binding method. In this way, you can create a atomistic package and explore the atomistic package also. Now, let's move to the next example where we create the FD-SOI builder option. In the last class, we sent the OS file, single quantum dot fully depleted silicon insulator OS file. Please import this one, OS file. You see. Download this OS file, single quantum dot. Copy this one. And in the hands-on training, paste here. Single quantum dot fully depleted silicon insulator OS file. This is designed in the directly in the K layout. And if you have a K layout, you can visualize also this file. Let me move further for the PPT and show the FD-SOI, how to do fully depleted silicon insulator. Now, basically, in this example, we go through the fully depleted silicon insulator quantum dot simulation. And in this simulation, we create a 2D layout in the K layout. And after that, in the importing in the OS module, in the QTCAD builder option, we create a proper heterostructure and create a fully depleted silicon insulator quantum dot model, where we find the electrostatic potential, conduction band profile, discrete energy level of a confined quantum dot, wave function, and you can see the workflow here also. First, we create a 2D layout in the K layout, and we export in the OS format. After that, we introduce the OS file in the QTCAD builder option through the Python code and create a mesh file in the .mesh file and .xao file. After that, we introduce the Poisson solver, where we find the electrostatic properties like the conduction band age, and we confine the electron also, like single particles. And we introduce the Schrodinger solver to find the quantum states, like the geometric property of quantum dot and the discrete energy level, basically. And we can see the key result, this type of key result, like conduction band profile, ground state, first excited state, and second excited states. Like here you can see, if you import this 2D layout from the OS file, you can see in the K layout, you can see the structure look like this. After that, to the QTCAD builder option, we create a proper heterostructure like this, where you have to introduce the plunger gate, barrier gate, gate oxide, silicon channel, box oxide, and back gate. And in the 3D key dimension, you can see you can introduce a nanometer size, like 2 nanometer, 10 nanometer. And after that, we introduce a material also, like for all the plunger gate, barrier gate, and the channel also. Like here you can see the proper workflow. First, we have to create a layout in the K layout. We already sent the OS file. So first step, skip the step. After that, we create a QTCAD builder option where we have to introduce the heterostructure stack for the FD-SOI and create a mesh size. And after that, we introduce the mesh size. We create a mesh file and move to the QTCAD option where we introduce the Poisson solver and Schrodinger solver. And we find parameters like conduction band profile. And through the Schrodinger solver parameter, we find the quantum confinement and their geometry property of quantum dot. Let's move to the again example. Save this one and close this one. Again, in hands-on training section, click on this and type FD-SOI builder dot IPYNB, and once we create, okay, after the session we'll share the all resources like other example also, like for the supercapacitors, superconducting qubits also, like where you introduce the find the EPR also, energy proportion ratio, and capacitance matrix, and Maxwell eigenmodes also, and we share the presentation and documentation also after the session. Now let's import some library here to create a proper device for the fully depleted silicon insulator. For that, we have to introduce QTCAD builder option from. First, select the kernel here, QTCAD, and from QTCAD builder, we have to import a builder option. Again, from the path live, to define the path, import path, and run this. Okay, and now add port cell again, and we have to define the path here. Now we have to define the layout path. Once we define the layout path, we have to import the mesh path also to define where we have to store the mesh. For that, we have to choose a mesh path. Same for the XAO also, which is used for the like adaptive meshing algorithm. Like if you want to introduce the adaptive meshing, you can use you have to use the XAO file from the mesh structure. Now run this again. Can you show me the issue? After that, we have to add the other code cell, and now we have to define the dimension of a growth along the z-axis, like for the fully depleted silicon structure. And from the 2D layout, we have to create a proper heterostructure, like to define the oxide layer on the top of channel and channel thickness. We have to define these things. For that, we have to introduce the gate oxide thickness. And box thickness. And we also determine the characteristic length of the mesh for the entire device. For that, we have to introduce the length also. Run this again, and now again add the code cell here. Now we have to initialize the builder object to load the layout file basically. Mm, Basically, it use the OS file to create a heterostructure. For that, we have to introduce the builder option here. We have to give the name also. And now we have to load the layout also. We have to define the path here, file path. Once you import the layout path, we have to run this solution. Let me see again. Copy this OS file and give the path here, and run this again.
I think you have a different name or something.
Let me check first. We have to give the proper path here, like for the script directory. It directly take from the parent path. That's why I have to paste the OS file here directly in the QTCAD folder. And once it's done, it loading the zip with the name domain also and the spacer also. Now it's completed. Again, add the code section here. And now we have to print the mask tree here basically. You can see the layout also, like domain, dot region, spacer, drain, and channel, which is defined in the 2D layout. We have to write this command to see the proper mask tree here, like the for the polygon, spacer, source, and drain channel. Again, add the code cell. And now we have to grow the structure from bottom to the top, like define the device domain. We have to define the silicon thin film layer. We have to define the top gate surface and the back gate also. For that, we have to create a proper heterostructure stack, and we have to use the mask. And we have to set the mesh characteristic length here, which is defined 10 at the top. And we have to run this. Now it's completed. We have to write VD use mask to set the mesh size also with the characteristic length 10, which defined earlier. Now we have to add the other code cell. And we have to grow the purine oxide layer to create a thickness of the box sticks. Again, we have to use the same function. And now you have to use the copy mask. And we have to give the name here. Box. And we have to rename the shape also. And we have to extrude basically. And run this again, this code. You can see it create a new physical group, dimension 2, with the box bottom, box side, box top, and box structure. Basically, it create a extrude. Basically, from the 2D layout, it create a 3D layout with the buried oxide, and it gave the name also like box bottom, box side, box top also. Now again, add the code cell. And we have to define the silicon thin film layer. You can see the in fully depleted silicon-on-insulator. After the box, we introduce the proper silicon thin film layer. Again, we have to use the BD use function. And again, we have to extrude also. and run this again. Now you can see it also create the silicon thin film layer with the physical group also. You can see creating new physical group dimension 2 with the spacer group. And you can see the drain side, drain bottom, drain top, drain also. Again add the coat cell to grow the gate oxide layer. For that, again we have to use the same function, use mask, and we have to create the oxide layer using gate oxide, and we have to extrude basically desired thickness. We have to copy the mask. Gate oxide, and we have to rename this gate oxide. And now we have to extrude basically, and again run this one. After that, it create a gate oxide region also in the above the thin film layer. And now we have to add the top gate surface where we have to introduce different top gate. For that, we have to use again same function, and we have to introduce the top gate here. We have to add the surface here and run this again. Now it create the top gate also and with the surface also. And we have to add the back gate also. After introducing the back gate, we have to save the mesh file. And we have to copy the function here. Back gate, and we have to rename also, and we have to extrude add surface also here, bd dot add surface, and run this again. Now in the last, we have to save the mesh file and visualize also. Let me show you for the film structure here. bd dot extrude film thick, we assign the function here. Now at the last, we have to save the mesh file and visualize also. Now we have to show the mesh file with the command bd.mesh. And we have to write the mesh file. And we have to give the mesh path here. And XO path also here. And for bd.view to visualize the in the GMS software directly. Run this. Let me show some error. Now you can see the structure here. Here you can see the fully depleted silicon insulator. First, this is a 2D layer at the bottom 2D layer. After that, we create a oxide layer, then thin silicon thin film layer, then top oxide. After that, we introduce some gate also here and create a 3D mesh structure. You can see here. And if we show the 1D structure, you can see the 1D structure, and you can see the physical group also. Tool, option, geometry, physical name. Now you can see the physical name here, like box oxide, spacer, channel region, barrier gate. You can see the barrier gate here also. Oxide top, gate oxide, and drain bottom. Once you create through the GUI option, it is very hard to assign the name also. So that through the QTCAD builder option, basically you have to use some function command to extrude and give the physical name. Close this. And now see the mesh file structure also. You can see at this path it saved the mesh file in the starting because I define wrong path. That's why it shows the mesh file here and XO file here. Copy this both file, Control C, and in hands-on training paste the file here. I hope everyone completed up to here and get their mesh file and .xao file also. And after the session, I'll share all these Python file like Jupyter Notebook also, where we introduce the like FD-SOI builder and Poisson solver also, and finding the lever arm matrix solver, Coulomb blockade, and charge distributed diagram also. Okay, now it's completed the builder option, which means in this Python code, we basically create a proper FD-SOI with the mesh file. Now, the next thing is we have to introduce the solver here, like Poisson solver and Schrodinger solver, to find some parameters like single quantum dot, double quantum dot region. Here you can see from QTCAD builder, we import a builder option and we skip to the save the path file for the single quantum dot fully depleted silicon insulator. Same for the .xo file, and we load the layout also. And I'll share the all this Python file. For the time being, I directly show the code here. No need to write or go through the hands-on training. I'll share the code directly. Let me open the builder option again. Close this folder. And let me open for the tutorial screen notebooks. And this is the example we created, like 3D model for the fully depleted silicon insulator quantum dot with QTCAD builder option. And you can see some theory part given here, Like in this tutorial, we basically introduced the fully depleted silicon insulator, which widely used in the nanoscale electronics. And you can see the paper also, like a recent industrial demonstration is this technology with the CMOS quantum computing, quantum dot, and by using our software. You can see the paper also by clicking on this. And you can see the graph here, basically figure for this FD-SOI, like the barrier gate, plunger gate, to create a quantum dot region to confine an electron or any particles. And after that, we introduce the material stack. You can see the material here also, like HFO2 for the dielectric gate insulation. And we introduce the 10 nanometer silicon layer and butyric oxide also. And it create a dot region here. And here you can see the device geometry option. Like if you want to create a design, you have to install the K layout. Here you can see the K layout. First, we have to design the required geometry file in the K layout, and you have to assign the parameters like plunger gate, barrier gate. You can see add a shape name properties. Like here you can see it introduce the barrier gate name. And once you complete the K layout in OS file, you have to move to the builder option. You can see QTCAD builder option, and we assign the layout path for the single quantum dot fully depleted silicon insulator OS file. And after that, we introduce the thickness label and the length also. And you can see the print the layout structure. And after that, you can see the growth the structure from bottom to the top. Once it completed, we introduce the Schrodinger and Poisson solver for the fully depleted silicon insulator for the single quantum dot region. First, we import some important libraries like Schrodinger and Poisson solver parameters. And same from the device package, we import constant module, material analysis module. And we define the path here. And after that, we introduce the gate bias value here. And we visualize basically. And here you can see we give the conference carrier uh, like electron. You can change to the holes also. Like at the top section, you can see the type of charge carrier in the quantum mechanical. You can choose the electron or holes also. If you go with the default version, default, it will give the electron. And you can set the temperature also like 0.1 Kelvin. And you can assign any temperature because QTCAD support cryogenic temperature. And you can see the material assigning here like silicon dioxide. And we introduce the boundary condition. You can see some theory part here. And we create a dot region. And we introduce a nonlinear Poisson electrostatics to find the conduction band edge and confinement potential. Let's run this all code. Let me clear all output. Okay, let me give the mesh file here. Let me choose the first environment first for the QTCAD. Now run this single quantum dot. Now it's load the mesh file here also. You can see here now. You can see the proper structure for the fully depleted silicon-on-insulator with the name box, spacers, source, drain, channel, and gate oxide also. After that, we create a device structure and assign the temperature also and material here. And here you can see the structure again with the material and the region also. After that, we use the non-linear Poisson equation to solve. Here you can see some Poisson iteration, and here you can see the conduction bandage to create a proper potential well. And here you can see the confinement potential. And we plot some function here. Like here you can see Schrodinger.BTU format. You can visualize in the directly in the para view. And now you can see the ground state, first excited state, and second excited state. For a time being, let me show you the one simple example for the superconducting circuits also. Let me close this one. In this example, basically use the 2D chip layout. Again, we design the layout in the K layout first. And after that, we to the builder option, we extract the heterostructure and Josephson atomic feature also using find the energy population ratio analysis using QTCAD software. First, we have to create the 3D geometry generation through the QTCAD builder option. And after that, we use the Joseph energy solver to find the properties also. And you use the electromagnetic simulation and energy proportion ratio analysis also in this example. Like to create this 2D layout design, like transform layout chip OS file. First, we have to design in the K layout. First we have to import some module here. You can see here. And here you can see we already given the OS file. In this path, we directly have a OS file here. You can see. And after that, we have to create a 3D geometry generation with builder option by defining the some thickness and path here. and extrude the air and substrate chip holder also. Let's all code. It's a environment here, and you get result here. First, we have from the 2D layout to the QTCAD builder option. We create a proper superconducting circuits here and find the Joseph junction also. Here you can see from the GMS, and now we use the Joseph energy variability also. Now you can see we initialize the builder option and give the name qubit also, and length unit you can see here. And you can see the mask tree here. And we displace the existing 3D region. It is still running. It will take some time. Let me change the system here. It will take some time. And here you can see some of the result here, like for the electromagnetic field here and log scale and energy participation ratio analysis you can also see. And let me show you some of the result also here. Like some of the GMS K layout junction. Like for this electromagnetic and EPR also. And if you see the documentation here, like superconducting, you can see linear Poisson equation solver, capacitance matrix. You can do the Maxwell eigenmodes, energy participation ratio method, and Joseph energy solver. And if you click on the tutorial option, you can see in the superconducting circuit device package, quantum metal workflow, like with the QSKIT and the Joseph junction. Like if I click on this, You can see, you can find this type of property also, like distribution of Joseph energy for 500 sample, 5,000 samples, sorry. And you can find like intensity plot for the aluminum here, interface associated with the Joseph junction simulated result. In this way, you can do for the spin qubit also and for the superconducting circuits also. And for the QTCAD builder option, you can click on the QTCAD builder to see the example and packages here, like how to construct the any structure here, like for any device structure. Like here you can see some tutorial given also for the gated quantum dot and for the advanced feature here you can see to create this type of a structure, how to create through the QTCAD builder option. Like this one, how to create this type of a structure through the QTCAD builder option. You can download this by Jupyter notebook also. You can see the package here and their function and their default value and their operations. For up to now, if anyone have doubt, please ask. And apart from that, like if someone working on the material science and like working on the DFT based software, if they are interested in the DFT based, they can directly connect with us. We can give the trial version for the DFT based software also. Like if you want to find the nano device properties, like DFT based electronic properties, mechanical properties, optical properties for any material, and finding the transport properties also, like transmission spectrum, trans channel, IV curve, photocurrent, different type of property. You can find through the different software, like through the NanoDecal, Rescue, and DSPO also. And you can visit the YouTube channel also for the Impulse Technology to see the playlist, and you can see the different software also, like PDF, DSPO, Laos tutorial, QTCAD you can see, and QTCAD project, SetFOS, Device Studio, Rescue software, and NanoDecal also. Like if someone facing an issue regarding the QTCAD software, you can watch the playlist also for the QTCAD. And your license is valid up to 1 month. And explore the QTCAD software, like for creating the spin qubit devices and so for the superconducting circuits and finding the quantum mechanical properties, and also use the adaptive meshing algorithm and superconducting circuits, all type of feature in the QTCAD software. And apart from that, if you need the help for the creation of any geometry file, like for the FIN-FET, for the MOSFET and other structures, you can directly connect with us. We can give the geometry file also.